I think in the last class we have seen the area property, did we? That if Fourier series, the signal f of t has the Fourier transform as f of omega, then the area of f of t is given by capital F of 0. Capital F of 0. So we will find the Fourier transform and then put the value of omega equal to 0. That will give you the area of f of t. Now can you please tell me what would be the area of f of omega? If we approach by the same way, then what would be the area of f of omega? Very good. So it is 2 pi multiplied by small f of 0. This comes from the inverse Fourier transform, right? So the inverse Fourier transform, as you all know, the formula is f of t is equal to 1 by 2 pi integral minus infinity to infinity f of omega e power j omega t d omega. So if you put t equal to 0, then f of 0 will be equal to 1 by 2 pi integral minus infinity to infinity f of omega. If I put t equal to 0, this term will become equal to 1 d omega. So which implies that the area of f of omega is equal to the of 2 pi multiplied by f of 0. It is equal to 2 pi multiplied by small f of 0. Next, okay, so we will have energy of signal, because predominantly we will be seeing the signals which are energy signals in the case of Fourier transform. So therefore, the energy of the signal can be calculated. We know the formula in the case of time domain, right? What is the formula in the time domain? Energy is given by integral minus infinity to infinity mod of f of t whole square dt, correct? So the energy of the signal is given by integral minus infinity to infinity mod of f of t whole square dt. Now if I use in the frequency domain, it is given by 1 by 2 pi integral minus infinity to infinity mod of f of omega whole square d omega. It's going to be 1 by 2 pi integral minus infinity to infinity mod of f of omega whole square d omega. So this is nothing but the energy of the signal. This is the energy of signal. Okay. So we say that mod of f of omega whole square is what we call as a energy spectral density. This is what we call as the energy spectral density. Next, please write down frequency response of the system. Frequency response of LTI system. Right. So let us consider an LTI system. So LTI is nothing but linear time invariant system. If I consider the input to be x of t, the impulse response of the system, let us consider it as h of t, and the output is y of t. So the input is x of t and the output is y of t, and the impulse response of the system is given by h of t. If I consider, as we all know, that the output y of t is nothing but x of t convolved with h of t, right? The output y of t is equal to x of t convolved with of h of t. I can write now the Fourier transform of x of t as x of omega, correct? And the Fourier transform of h of t as h of omega, and the Fourier transform of y of t as y of omega. Now naturally, what should be the relation? What should be the relation between x, h and y? Y of omega will be equal to x of omega. Convolution in the frequency domain is going to become, the convolution in the frequency domain is going to become multiplication, and h of t is now going to become h of omega. So basically the arrow marks indicates the conversion into frequency domain, right? So now I can say that the output Fourier transform, which is y of omega, is equal to x of omega multiplied by h of omega. Then what is h of omega? What is h of omega? H of omega is given by y of omega divided by x of omega. H of omega is equal to y of omega divided by x of omega. This h of omega is what we call as the frequency response of the LTI system. H of omega is what we call as frequency response. I can say h of omega as frequency response of LTI system. H of omega as the frequency response of LTI system. Okay? Right? Then what is mod of h of omega? What is mod of h of omega? Mod of h of omega is what we call as a magnitude response of the LTI system. Magnitude response of LTI system. Magnitude response of LTI system. And angle of h of omega, is what we call as a phase response of LTI system. Okay? So h of omega is nothing but the ratio of y of omega to the top x of omega. Y of omega to the top x of omega. We call it as a frequency response of an LTI system, whose magnitude is what we call as a magnitude response, and its phase we call it as a phase response. So what I am doing here is that we are going to see the systems, LTI systems response for the sinusoidal input. If you remember, one of the students has asked, sir, we have seen for impulse, what is the response? We have seen for a step, what is the response? Now, what is the response in the case of a sinusoidal input, right? What is the response in the case of a sinusoidal input? That is what we are going to learn now. The response of an LTI system for sinusoidal input. So, whenever you apply the input as sinusoid, the result will also be a sinusoid with some phase and magnitude shift. With some phase and magnitude change. Right? So, for example, if I am considering here a into cos omega naught t as an input, then my output y of t will be equal to, for this corresponding input, the output will be, when you are passing through the system, the output will be a multiplied by m multiplied by cos omega naught t plus phi. Okay? If I give a sin omega naught t, passing through the system, the output will be a multiplied by m multiplied by sin omega naught t plus phi. And when I talk about a e power j omega naught t passing through the system, I will have the output as a multiplied by m multiplied by e power j omega naught t plus phi. So what is happening here? When you are passing your sinusoidal input through the system, which is LTI system, the output is also sinusoid with some change in the magnitude and with some change in the phase. With some change in the magnitude and with some change in the phase. Now what is this m called as? This m is nothing but magnitude of h of omega, which is nothing but the magnitude response that we have seen in this particular case, right? Magnitude response at omega is equal to omega naught. What is omega naught? Omega naught is the frequency that you have applied at the input. Okay? For example, if you are talking about cos omega naught t, the frequency is nothing but omega naught. So this m is nothing but the magnitude response at the frequency of omega is equal to omega naught. This is nothing but the input frequency that you have applied, which is omega naught, right? Similarly, phi, the phase, is equal to the of angle of h of omega. It is angle of h of omega at omega equal to omega naught. Okay, so this is the magnitude part and this is the phase part. So m is equal to mod of h of omega at omega equal to omega naught, and phi is the phase of h of omega at omega is equal to omega naught. Okay, so what is the change we are having is that you will be having some manipulation in the amplitude, that whatever initial amplitude was there, that is now going to be multiplied with m. That is now going to be multiplied with m, where m is nothing but the magnitude response at the input frequency. Similarly, phi is also the phase response at the input frequency. Now, this is one concept which is not only important in signals and systems, this will also be helpful in control systems, because even in control systems, we will be applying all these inputs that we have learned, whether it is a delta, whether it is a unit step, whether it is a sinusoidal. Okay, even in fact, there you will also see for the ramp also, but not very importantly, but you will also see for the ramp also, right? So this part is very, very important. M has to be a real part, right? If you are taking a magnitude of any number, it should be a real one. If you are talking about h of omega, I would have said that it can be real, it can also be imaginary. I mean complex, right? But if you are talking about m, what is m? It's a magnitude, and magnitude is always real, yes or no? So let us talk about a distortionless system. Distortionless LTI system. Can you please tell me what is the meaning of distortion? What is the meaning of distortion? If I take a particular system, which is of course an LTI system, I am giving the input as x of t, and the output of the system is y of t. Now when I say that this system is distortionless, if I mention that this system is distortionless, so the major importance of distortionless system is that its shape is not going to change. Its shape is not going to change. It means if I give a sinusoid here, it remains a sinusoid. If I give a square pulse here, it remains a square pulse. There can be a change in the magnitude, that it can be small, it can become big, or there can also be a phase difference, phase shift. I mean to say that is a time shift. So it can be shifted in time, or it can also be changed in terms of the magnitude. But the other part, the actual information should not change. Actual information should not change. So when we say there is distortion, then what we are referring to is that its shape of the information has changed. Okay, so if the shape is changing, it means that your information is distorted. If the shape of the information has changed, okay, then we call that as a distortion, right? So when I say that y of t is the output for a distortionless system, you can definitely have a change in the magnitude. So initially it is x of t, now it's becoming k multiplied by x of t, and there can also be a phase shift. There can also be a phase shift. Okay, in a general case, we will be having, when you are passing through the system, the output will generally be delayed. Okay, I'm talking about a general case. Okay, in a general case, when you are passing your input called as x of t, it is generally going to be delayed. Unless and until you are using an advancing system, whatever function this particular system is doing, your output will be a delayed when compared to that of your input. So by this aspect, I'm considering that k multiplied by x of t minus t naught. It means that here I'm allowing the magnitude to change, and I'm also allowing some amount of delay which is present because you're passing through the system. Because you're passing through the system, so I'm allowing some delay, and also I'm allowing some change in the magnitude. I'm also allowing some change in the magnitude. So y of t is equal to k multiplied by x of t minus t naught. Now let me apply Fourier transform on both sides. So if I consider y of t is equal to k multiplied by x of t minus t naught. Now when I apply Fourier transform on both sides, so then we will be having y of omega is equal to k multiplied by e power minus j omega t naught, k multiplied by e power minus j omega t naught into x of omega. I am sure you have understood from where we got this term. Have you understood this particular term, from where we got this particular term? we apply Fourier transform, so it becomes y of omega. This side, if I apply Fourier transform on x of t, it is x of omega. On x of t minus t naught, according to the time shifting property of the Fourier transform, it's going to be x of omega multiplied by e power minus j omega t naught. Okay, because from the time shifting property of the Fourier transform, we are getting this particular thing. Now, if I want to find h of omega, I will take x of omega to this particular side. Then I will be having h of omega which is given by k multiplied by e power minus j omega t naught. H of omega, which is nothing but y of omega divided by x of omega, is equal to that of k multiplied by e power minus j omega t naught. H of omega is equal to k multiplied by e power minus j omega t naught. This is what we call as h of omega, the frequency response of the system. Now, if you see the magnitude, if I see the magnitude response, mod of h of omega, this is equal to the constant k. This is equal to the constant k. And if I take the phase of h of omega, see, this is nothing like a polar form, right? You are having a complex number, having a magnitude and having a phase. Okay, so I'm writing it as k here, and here it's going to be e power minus j omega t naught. Okay, so e power minus j omega t naught. So what it's going to become? The phase is going to become minus omega t naught. In a polar form, if I can write it as r e power j theta, I call r is nothing but the magnitude and theta is nothing but the phase. So here you will be having the magnitude which is going to be equal to k only, but the phase over here will be equal to minus omega t naught. The phase over here will be equal to minus omega t naught. Now if you plot the graph, mod of h of omega with respect to frequency, what you will be seeing? That the magnitude is not disturbed with respect to frequency. Now as the frequency is changing, my magnitude is remaining as constant. Now when I talk about the phase, the angle of h of omega, so the angle of h of omega, it is like a line, right? Y is equal to m multiplied by x. Okay, because your y is nothing but the y-axis, x is nothing but your omega. Yes or no? Your x is nothing but omega. Yes or no? So you will be having something like y is equal to m multiplied by x. It's like a line. Correct? So when it is a line, then what is the slope? Y is equal to m multiplied by x. So the slope is going to be minus t naught. The slope is going to be minus t naught, indicating that it's a negative slope and passing through the origin. Okay, it's a line with a negative slope passing through the origin. So the slope here of this line, is equal to minus t naught. The slope of this line is equal to minus t naught. So if you see the magnitude response is constant, and if you see the phase response is equal to minus t naught, having a slope of minus t naught. Can I say the magnitude response is constant and the phase response is linear? Can I say the magnitude response is constant and phase response is linear? Okay, so whenever I talk about the distortionless LTI system, always its magnitude response is going to be constant. And its phase response is going to be linear. See, if I consider advancing, then what would happen? If I consider advancing here, in that case it will become plus here. So if it becomes plus here, it would be the same line plus t naught omega. Okay, now the slope would become something like this. It means that instead of having a negative slope, you would have had the positive slope. you would have had the positive slope. That is the difference. So whatever be the case, whether it's an advancing or a delay, why I am considering delay? I am considering a delay here because of the fact that generally you will be having a delay. Generally you will be having a delay. Advancing will only be in a very specific cases. But in a general case, we know that it's logical enough that whenever you are passing your input through the system, the output will be the delayed version of the input. Always. There will be some amount of delay. So therefore I am considering the general case here. Now the slope that I got here, okay, it's going to be a constant. It means that it's a line. So I can say that every distortionless system will have a phase response which is linear and the magnitude response which is going to be a constant. So whenever there is no magnitude distortion, whenever there is no magnitude distortion, in that case your magnitude is going to be a constant. So please take the question on your secondary screen. I think secondary screen is visible to all of you. So in this question, if you understand, the frequency response is given and the question is about the step response. The frequency response is given and the question is about the step response. There in terms of f, okay, because whenever you're talking in terms of frequency domain, generally it will be in terms of omega as far as literature is concerned, but sometimes you can also see f. But fortunately we know the relation between f and omega, right? The simple relation between f and omega is that omega is equal to the term of 2 pi multiplied by f. Okay, so h of f is something like this. And what is h of f? It's the frequency response of the system. So if h of t is the impulse response, its Fourier transform will be the frequency response. So either we write it in terms of omega or in terms of f. Now this is something which is given as phi by 1 plus 10 pi f. Or if you want to write in terms of omega, it is phi by 1 plus 2 pi multiplied by f. I can write it as omega. You will be having 5 here. You will be having 5 here. So it is going to be, I think there is a j which is missing, right? So there is a j over here. So I can take 5 as common. So it is going to become 1 by omega. 1 by 5 plus j omega. It is 1 by 5 plus j omega. So h of f is or h of omega is given as 1 by a plus j omega. H of f is given as 1 by a plus j omega. Then what is h of t going to be? It's a standard function. According to the standard function, it is going to be e power minus 1 by 5t u of t. Okay, so h of t is equal to e power minus 1 by 5t u of t. Impulse response is given. Now step response is asked. If impulse response is given and step response is asked, we know the relation between impulse response and step response. We have learned this in the second chapter, LDA systems. The step response will be the integration of the impulse response. Integration of the impulse response. Okay. Ultimately, we'll end with it of u of t. So 5 into 1 minus e power minus 1 by 5t into u of t. So the answer which is matching here is option B. Why I have put u of t? I have put u of t because here I have blindly considered t as positive, right? I have blindly considered t as positive. So when I have taken integral minus infinity to 0 to t, I have taken it for the reason that I am considering my value of t to be positive. If my t value is negative, if t value is negative, in that region my u of t value is going to be 0. Okay, so whatever answer that you are getting will be applicable only when your t is positive. If your t is negative, then the entire integration is going to become 0 because of the presence of u of t. U of t is something which is applicable only for t greater than 0. So to make it clear that this is applicable only for t greater than 0, I will write u of t. So in all the cases wherever that the answer is applicable only for t greater than 0, there we will write u of t at the end. I'm sure it is clear now. Let us go for the next question. Okay, so here h of omega is given as in the form of polar form, having a magnitude of this one and the phase of minus tan inverse of omega. And your system is an LTI system. the input of the system which is given as sin t and the output is asked. What we know is that whatever input, if it is sin t, amplitude is going to become m now. Initially it was 1, now it is going to become m into 1, which is m itself, into sine of t plus some phase. Sine of t plus some phase. So in a standard form we have taken a sine omega naught t as an input. So a is 1 here and omega naught is also 1 in this case. Omega naught is also 1 in this particular case, yes or no? Omega naught is 1 radian per second, right? So here m value and phi value have to be found out. M value and the phi value have to be found out. What is the m value? M is nothing but 1 by under root of 1 plus omega square. 1 by under root of 1 plus omega square at omega not equal to 1, or omega is equal to omega not equal to 1. Omega is equal to omega not equal to 1. So it is going to become 1 by root 2. It's going to become 1 by root 2. And what about the phase value? The phase value is equal to minus tan inverse omega. Minus tan inverse omega. Minus of tan inverse 1 is what? Tan inverse 1 is pi by 4. So you'll be having the phase which is given by minus pi by 4. The phase is given by minus pi by 4. So you can substitute here. It's going to be 1 by root 2 sine of t minus pi by 4. Okay, which is nothing but our option D. See how omega is equal to 1. If you remember, in the previous case, so whenever we have substituted, okay, and we have written m, what is m? M is nothing but h, magnitude of h of omega, magnitude of omega, magnitude of h of omega at omega is equal to omega naught. Yes or no? Go back and see. When we have written m, in this case it is going to be mod of h of omega at omega is equal to omega naught. What is omega naught? Omega naught is 1. So therefore we are substituting 1 here. Because the value of omega naught is 1, omega is equal to omega naught. Omega naught itself is 1. If you substitute, it's going to be 1 by root 2. Okay, and same here also I am substituting omega equal to 1. This becomes pi by 4, so minus pi by 4. See how omega naught is equal to 1? Because what is the frequency value here? When you write sine omega naught t, omega naught is the angular frequency, right? When you write sine omega naught t, omega naught is the angular frequency. Now what is the value of omega naught here? If nothing is there, then we can consider it as 1, yes or no? If nothing is present here, can I not consider it as 1?